This video I'm hoping to present to us some of the basics of the relationships between hydronium ions, hydroxide ions, the activity of those, and how that relates to pH and pOH and the relationships that exist between all four of those variables. And then connect that to a specific type of solution that we may have when we need to consider activity versus maybe we don't need to think about the difference between activity and actual concentrations. But we want to first focus on these relationships that are foundational for us understanding how our pH is influenced by the addition of a solute. And so we're going to identify what kinds of solutes to focus on, how that relates to activity in this video here. So first, let's go ahead and start with the relationships that we want to focus on. So here we have our pH, and a pH is a measurement of the hydrogen ion or hydronium ion concentration, specifically its activity. And this is important once we get to start getting to higher ionic strength solutions, 10 to the negative fourth, 10 to the negative third, or higher, where we start to see this deviation from the actual concentration to the activity of those ions. And again, we can break that out into the relationship between our activity and our hydrogen ion concentration. Again, reminding us whenever we write hydrogen ion, we also mean hydronium. It's really a hydronium. There's really no such thing as a floating proton in solution. We also have the ability to go back and forth. So if I know my pH, I can solve for the activity of the hydrogen ion, if I know our pOH, we can solve for the activity of the hydroxide ion. Now, reminding us whenever we have lowercase p followed by something that just means negative log, in this case, the negative log of our hydroxide ion concentration. And we see that those two distinct relationships, the activity of our hydrogen ion and hydroxide ion concentrations, is equal to Kw. Now, Kw we typically think of as 1 times 10 to the negative 14th. It's an equilibrium constant. Like any other equilibrium constant, it is temperature dependent. So if our temperature changes, it's going to be different than that 1 times 10 to the negative 14th. But if we have a temperature of 25 degrees Celsius, that's our equilibrium constant we can use. Again, remember that's the equilibria where we have water undergoing this auto-ionization into the hydronium and hydroxide ions. Our equilibrium constant for that reaction is our Kw, our water auto-ionization constant. That reaction here is always happening in solution. That reaction will always happen in any aqueous solution. The relative amounts of H plus and OH minus can be different depending on if we add something else that also influences those relative concentrations. We also know the sum of our pH and pOH is 14. And so we have all of these different relationships that give us the ability to identify the activity of H plus or OH minus and how that relates to our pH. Now, if we just look at this is just kind of a good baseline for us in our thought processes of how much H3O plus and OH minus we have in solution at 25 degrees Celsius. If it's just pure water, we're going to have a concentration of 1 times 10 to the negative 7th for each of those. And they would be equal to each other in that neutral solution. Now, if we add something that something else that also produces OH minus or H plus or H3O plus in solution, that's going to throw off the balance between them. And that's where we add an acid that is better than water, or a base that is a better base than water. And that's going to influence the relative amounts of those. So we first started with strong acids, strong bases, and that's what we're going to start with here, and then we're going to move on to weak acids and weak bases and see how they relate back to our water reactions. So here we have an example. We're going to work through an example applying some of these concepts, and then I'm going to give you a chance to practice it. So our first example here is that we want to find out the pH. So if we have pH, that means I need to either find out the activity of the H plus ion or the activity of our hydroxide ion. Either one of those is going to get us to the ability to find our pH. We want to find the pH of an aqueous solution that contains 5.8 times 10 to the negative 6 molarity nitric acid and 0.075 molarity KBr. So we have both of those solutes present in our solution. We are told that our nitric acid is a strong acid. We can identify that as well. If we look and we would find a Ka value that is small for that, and we would see that it is an acid that in water will be fully ionized. And then we have our potassium bromide is also very soluble. So what does that mean for us in solution for these two species? If we know that nitric acid is a strong acid, that means it undergoes this 100% ionization where we react it with water and it gives us H3O plus and then the nitrate ion. And again, reminding us we can also shorthand it as this H plus. We can use those interchangeably. So that's what we would see for our nitric acid. Then we also have where our potassium bromide is very soluble, meaning it undergoes this 100% dissociation into our potassium and bromide ions. So if we have both of those ions present in solution, whatever amount of potassium bromide I start with, all of that exists in solution as K plus and Br minus ions. So if I started with 0.0750 molarity KBr, what that means is I'm going to get a 1-to-1 dissociation for that, 0.075 molarity K plus as well as 0.0750 molarity Br minus. It dissociates in this 1-to-1 ratio for our KBr to K plus and Br minus. So now we have those K plus, those Br minus ions in solution. In addition, we also know that we have our nitric acid. And our nitric acid in that reaction is going to produce 5.8 times 10 to the negative 6 molarity nitrate ions and hydronium ions, both of those. And the reason why we say that that's equal to what we start with here, because it is a strong acid and it undergoes this 100% reaction. So now we have those two things in place. And if we're trying to identify our pH, we need to consider what else possibly may influence the amount of H plus or OH minus. And I'm just going to label this as reaction 1, 2, and reaction 3 here that's always happening is the reaction where we have water undergoing this auto-ionization inside of solution and to give us our hydronium and hydroxide ions. And again, this is our KWs, the activity of our H plus and OH minus. So now we look at these and we want to answer a few questions. Number one, is this reaction important or significant in producing H plus ions relative to what we added in our nitric acid? So that's the first question we want to ask ourselves. Let's answer that question before we move on to question 2. What we want to do is we want to think, okay, in general, if it was just pure water, water would give us about 1 times 10 to the negative 7th molarity H plus, right? If it's just pure water. Well, into that, I'm adding 58 times 10 to the negative 7th molarity, or 5.8 times 10 to the negative 6 molarity of H3O plus from our nitric acid. So we see that 1 is going to influence, that's about 2% of the amount that we added of our H3O plus. So we can't necessarily ignore the contribution that we possibly could have with water. Now the reason for that is because our concentration of our nitric acid, the amount of H3O plus produced from that, is fairly close to what we would get for water. So we can't just exclude that there. If this was maybe 5.8 times 10 to the negative 3rd or negative 4th, we would see that's so much greater than what we would possibly get from water. That's the predominant species. We don't even need to worry about this equilibrium with water. But what we do notice is that they are similar, so we do need to include that. That was question 1. Let's look at the implications of question 1. What that means is I cannot just say that all of the H plus comes from our HNO3. We don't have the ability to make that conclusion. And that's because some amount of it is coming from water as well that will significantly influence that. It's not negligible. Okay, so let's see, how do we apply how much of that we get? So in order for us to do that, we're going to look at our reaction here. So look at our initial change equilibrium for what we get. Again, we exclude our pure liquid. And we look here and we see, okay, if this was just pure water, I would say I didn't directly add in any other source of OH minus. I didn't directly add in any other source of H plus. However, we do have another source of H plus. We have this other 100% ionized nitric acid source, where we have 5.8 times 10 to the negative 6 molarity H plus from our nitric acid reaction. And so that means we're not starting at this 0 level, but we are going to produce some amount more, so some increased more, from this ionization reaction. And so we're going to end up getting an expression for some amount of our H plus being produced from water added to the amount we originally had with our nitric acid, and then some amount that's being produced of our hydroxide ion. So that was question 1. Now we have this set up here. We see there's some contribution from the water to produce H+. The second question that we need to answer is, when we think about our Kw or our pH, do we need to focus on the deviance between activity and actual concentration? Now what we mean by that, we remind ourselves the activity of H+ is the gamma value of H+ times the actual concentration of H+. We need to ask ourselves, is our gamma value, the activity coefficient, close to 1? Is it going to be to a place where there's almost no difference? And we remind ourselves, okay, well, what causes there to be a difference in the activity versus the actual concentration? For us to answer that, we need to figure out what is our ionic strength. And the ionic strength of our solution, remember, is the sum of all the ion charges present in the solution relative to the actual charge of those ions. And we need to figure out what the ionic strength is. That would tell us, is there any deviation? Is the ionic strength of the solution very small? Is it large? How would that tell us something about the deviance, so the gamma value, relative to for the actual concentration to the activity of that solution? And we see there's 2 primary components of our solution. Again, we looked at the reaction that we saw in reaction 1, the ionization of our nitric acid. Now we go to reaction 2 and we see I actually have 0.075 molarity of our potassium ions and 0.075 molarity of our bromide ions. A fairly significant amount, not negligible. And so then if we go ahead and we actually quantify our ionic strength here, we would find it's 0.750 molarity. I'm not going to go through the step-by-step of that. We've done that before. But we'd find that, okay, that's not negligible. That's not small. Maybe that will influence our gamma value. Remember we said an ionic strength of maybe 10 to the negative 5th, 10 to the negative 4, they're smaller. We're going to see that our gamma value is basically 1, and there's almost no deviation from the activity relative to the actual concentration, but we're much greater than that, so we're way above that. So then what we need to do is, now we've answered 1, we get some amount of H+ from water. 2, our activity is going to deviate from our actual concentration. So now let's apply that here. I'm going to express that by saying our Kw is our gamma value of H+ times our actual concentration of H+ times our activity coefficient of OH- times the actual concentration of our OH- ions. And so now we see, well, before we can actually take this and plug it in here, and this expression and plug it in here, we first need to figure out what are our gamma values. And again, we've used that Debye-Huckel equation. Say we did that and we calculated that, we would find the gamma value for H+ is going to be 0.837, and the gamma value of OH- is going to be 0.783. And so what that tells me is that I'm going to have a deviation or a reduction of the activity or behavior of those ions in solution relative to the actual concentrations. So now we can go ahead and include those in our expression up here. And so now we take all of those arrows and all that stuff together, and we end up getting an expression that looks like this. Our Kw, 1 times 10 to the negative 14th, equals our gamma value, our activity coefficient for H+, 0.837. The concentration that we expected for the actual concentration of our H+, 5.8 times 10 to the negative 6 plus X. Then we get our concentration, or excuse me, our activity coefficient for hydroxide, 0.783, times the actual concentration that we had for our expression, of our hydroxide ion. So now we have this one expression. We see we have our one unknown here, our how much of H+ and OH- we're making from our water. I'm not going to go through the algebra of this, but again, we have this would give us some kind of polynomial, secondary polynomial, which gives us two possible answers. We would get 2.52 times 10 to the negative 8th as an option, or negative 6.05 times 10 to the negative 7th as an option. We look at that, we say that's not a valid option because that would give us a negative concentration of OH minus, not possible. And so now we'd say that is our value that we would get there. Well, now once we have that, now we got to do some work into identifying some information relative to the pH now. So we could do this one of two ways, okay? So we have, let's think about what we know. We know the actual concentration of, we've been using H+, so let's keep it that way, is 2.52 times 10 to the negative 8th plus our 5.80 times 10 to the negative 6th. So that's our x plus the 5.8 times the negative 6th. We also know our concentration of hydroxide is 2.52 times 10 to the negative 8th. So there's one of two options that we could do here. We could use our H plus to find the activity of our H plus to then find our pH, right? We have those relationships that exist there. And then, or we could also say, well, let's find the activity of our OH minus to then go and find the activity of H plus to then find the pH, or to find the pOH and then our pH. So again, we see we have these multiple paths. They all get us to the same place. We have the same relationships that exist here. And so we can do any one of those. I'm going to post solutions to this in Canvas where you can actually look at any one of those options. And I'm just going to show us one of those options here. So let's go ahead and just do, maybe since we already have the concentration of our hydroxide, let's use that one. So we can find our pOH is the negative log of our activity of our OH minus ion. So that would be negative log of our activity coefficient for our hydroxide ion was 0.783 times 2.52 times 10 to the negative 8th. And after we do that, we're going to find that we would get a pOH of 7.705. And again, reminding us, just because of the way that logs work out in the calculations, we would get 3 total significant digits in our value that's inside of our log, which gives us 3 digits past the decimal place in what we calculate from that. I'm not going to go through the detail of that. Don't get overbogged with that, but that's just why I have 4 significant digits total in our pOH here. Then we can go ahead and find our pH as 14 minus 7.705 equals 6.295. So again, this makes sense. It's an acidic pH. We added an acid in a very small concentration, but again, it's not the same as it would have been if we would have ignored the contribution that we would have gotten from the water as part of our equilibrium here, the autoionization of water. So now that we've had a chance to maybe think through this, answer those questions about activity, the question about the contribution of water and its ionization reaction, why don't you go ahead and answer this question on your own. So pause the video after I read this and then go ahead and answer it and then come back and see what we did. So we want to find out the pH of an aqueous solution that contains 2.5 times 10 to the negative 3rd molarity potassium hydroxide and 0.05 molarity KCl. KCl and potassium hydroxide are both very soluble in water. So we want to ask ourselves what's going to influence our pH and what kind of reactions we'd have from there. So I want you to go ahead and pause the video and work through this on your own and then come back and see what we got. All right, so now that you had a chance to work through this, again, we answered the first question, do we need to think about activity? What is our ionic strength? We would find, after looking at the ionic strength contribution of our potassium ions and chloride ions from potassium chloride, and our potassium ions and hydroxide ions from our potassium hydroxide present in solution, we're going to get an ionic strength of 0.0525 molarity. From that, we would get these specific gamma values or activity coefficients for the H plus and OH minus ions. And so we see there is this deviation. We notice that these are not equal to 1. We have a fairly high ionic strength of our solution. Now, that's our first question. The second question is, what's going to influence our pH? Or maybe you ask yourself this first, right? We can go through either one of these steps. And see, we have our potassium hydroxide here. That's a strong base. It's going to produce a lot of potassium, a lot of hydroxide ions. It fully dissociates. And so because it fully dissociates, we're going to have a concentration of 2.5 times the negative third molarity from our potassium hydroxide dissociation. So we'd say, well, that's so much greater relative to the approximately 1 times 10 to the negative 7th molarity from our hydroxide, from water autoionization before we added this, right? So we see there's a very small amount that would possibly be contributed by the water molecules producing some amount of hydroxide. So effectively, we can't ignore that. And that's because we have such a larger concentration, 4 orders of magnitude, of our potassium hydroxide relative to our water, relative to what we would have possibly gotten from water in before we even added the potassium hydroxide. So that means we could take the concentration of our hydroxide ion to be the same as what we get from our potassium hydroxide. We just need to make sure we include the thought about our activity. Remember, our activity is going to reduce the amount of that. That's because we have a pretty good amount of potassium chloride and potassium hydroxide here. So now we can go ahead and find our POH, negative log of our activity. We get 2.695, and then our pH ends up being 11.305. So we see here that we have a fairly high pH. It's a strong base that we added into our solution, but we also needed to consider not just only our potassium hydroxide, but also the potassium chloride influence on our activity and how it reduces our activity coefficient of H plus and OH minus in our solution. So hopefully this gives us a little bit more exposure to acids and bases, strong bases in solution and activity. And then we're going to continue this discussion talking about weak acids and weak bases with activity.